In the last video, we were able to sketch a picture and illustrate how you can use the secant line to get your hands on the tangent line. And we did that by taking limits. And I want to emphasize to you that everything that we do in calculus comes down to limits. Won't always write things down in terms of limits, but limits are always behind the scenes. And so we're ready at this point for a formal definition. You've seen the picture behind this definition. So that we're going to define now the tangent line to a curve, f of x, at a specific x value is the line that goes through the point a, f of a, so it touches the curve at that point with slope. Remember, it all comes down to the slope. So with slope, m equals the limit as h goes to 0 of f of a plus h minus f of a all over h. And I need to add that when this limit exists. So if this limit doesn't exist, then there is no tangent line to this curve at this point. And that happens. We'll see examples of when that happens. We're going to be able to recognize that visually pretty quickly later on. Also want to give you some new notation. So we're going to call m being this m, the slope of the tangent line. We're going to call the slope of the tangent line, I think I have some things here. Slope of the tangent line, the derivative, sorry. I forgot that I needed to fill that in. Call the slope of the tangent line the derivative of our function at x equals a. And we're going to denote that by f prime of a. So this prime symbol means it's the derivative, which means it's the slope of the tangent line to the function at a. Well, before we do an example, I want to show you a different way you can write down this limit. It's actually the same thing, but we'll need to understand both. So last time we started at A. This was the point that we want the tangent line. I'm wanting to compute this tangent line. Last time we started here and we went for a walk and we said, look, walk a distance of h and you end up at A plus h. This time I want to start here and I want to just go out to an arbitrary x. So I have 2 points on my line and I can compute the secant line through those 2 points. No problem. That's a little bit of a bendy line. Let's see if we can straighten it up. Okay, close enough. So there's the secant line, and I can certainly compute the slope of the secant line. And so what I want you to realize is the derivative in this case is going to be the limit as x goes to a. Let's write it here. The secant line here is f of x minus f of a all over x minus a. This is going to, as x gets closer and closer and closer to a, it's exactly the same picture, right? You can imagine this point, and the tangent lines are getting closer and closer. Sorry, the secant lines are getting closer and closer and closer to the tangent line. So same story, it just looks different. So this limit is exactly the same thing as the limit as h goes to 0 of f of a plus h minus f of a all over h. And so that can be a little confusing for people because they look so different. And it might be helpful for you to realize that they're the same limit if you set x equal to a plus h. That's what we're doing. Before we went over to this was a plus h, we can also think of it as an arbitrary x, and depending on how you name it, depends on what your situation looks like. And so either one of these is f prime of a. These are the same limits. So typically when we're computing derivatives, we're going to use this form, but occasionally I'll need to come back to this one as well. But I want to make sure that we're comfortable with this. All right, well, let's stop the video here, and in the next video we'll work out an example together.